Welcome back. Let's learn about torsion of space curves. Alright, so previously in Calculus 3, we looked at how to find the curvature of space curves, which is a measurement of a curve's failure to be a line. But now there's another measure of curves that we are interested in, known as torsion. And we like to think of torsion as being the measure of the degree of twisting for a curve, or another way to think of it is a measure of a curve's failure to be contained in a plane. Alright, and so if you remember from the lesson on T and B frames, the unit binormal vector, vector b, describes the direction of twisting, but what we are interested in here with torsion is the amount or the intensity of that twisting. That's what we're going to measure when we measure torsion. And we represent torsion with the Greek letter tau. It sort of looks like a T with some extra curves in it. Okay? But thinking back to what torsion measures, which is the twisting of a curve or a curve's failure to be contained within a plane, if you consider a plane curve, like I have right here, a plane curve would have no torsion because the curve is entirely contained within a single plane. Right, this curve right here, that's represented by this vector function r of t, would be contained within the xy plane, and so it does not twist out of this plane whatsoever, hence the name plane curve. It is a curve in a plane, and so it doesn't twist out of that plane in any way, which means that there is no torsion. Okay, so a plane curve has zero torsion, which means that tau would be equal to 0, and it also means that the unit binormal vector would be a constant vector. Right, the unit binormal vector from our TMB frames that I mentioned earlier, it represents the direction of twisting for a curve at any point along that curve. And so if there is no torsion for a plane curve, or there is no twisting, then the direction of twisting would not be changing. The unit binormal vector would not change. It would remain constant for the entire curve, no matter what TMB frame you look at along it. Okay, but unlike a plane curve, a space curve can have torsion. There can and most likely will be some twisting in a space curve. And so if you consider this space curve that is in the shape of a helix in 3D space, this curve fails to be contained within a plane. All right, there is clearly some twisting going on with this curve, and so it does not remain contained within any plane, not the xy plane, not the xz plane, the yz plane, or any other plane within the 3D coordinate system. You cannot find one plane that would contain this entire curve. It is going to be twisting in and out of different planes as you move along that curve. All right, and so in this case, clearly the unit binormal vector would not be constant. The direction of twisting is going to be changing as you look at different TMB frames along this space curve. Okay, so the direction of twisting, which is represented by vector b, would be changing, but what we are interested in here with torsion is the measure of that twisting, the degree of that twisting at points along this curve. Because for a lot of curves, the torsion or the amount of twisting at different points along that curve will not be the same. There will be different amounts of twisting at different points along a curve, and so that's what we want to measure. That's what we are interested in with torsion. All right, and so mathematically, we define torsion like this. The torsion tau is equal to the change in the unit binormal vector with respect to the arc length in the opposite direction of the unit normal vector n. All right, so that looks like this. We have negative dB divided by ds dot the unit normal vector n. All right, now this might look a little confusing at first, but I am going to explain it. dB ds represents the derivative of our unit binormal vector with respect to the arc length parameter, or in other words, you can think of it as the change in the unit binormal vector with respect to the arc length. That's how I would interpret that. It is negative, and we'll get to that in a second, but you're going to take its dot product with the unit normal vector. And what that does is it measures the change in the unit binormal vector in the direction of the unit normal. But actually it's in the opposite direction of n because of the negative out front. All right, remember for vectors that a negative in front of that vector means that that vector would be pointing in the opposite direction of how it would normally point. Okay, so when you take the dot product of the derivative of the unit binormal vector with respect to s with the unit normal vector, which would also be in terms of s, What results is a measure of how much the change in the unit binormal is in the direction of that unit normal, but then would be in the opposite direction because of the negative sign. Okay, so that's the thinking behind this formula. That's what's equal to torsion, and it should make sense because the direction of twisting, the unit binormal vector, is related to the direction of turning, which is what the unit normal represents. The unit binormal vector rotates in the direction opposite of the unit normal vector when there is twisting. And so to demonstrate my point, I'm going to bring back the Lego plane from the lesson on TNB frames. Remember that a motion of twisting would be anything like this, where the plane twists back and forth. All right, that is our motion of twisting. Remember that the tail fin back here represents the direction of turning, or the unit normal vector. And for this demonstration, this wing right here will represent the direction of twisting, or our unit binormal vector. All right, notice that as the plane twists, that the direction that the tail fin is pointing, the unit normal, is the opposite of the way that the unit binormal is moving. All right, so if we twist this way, the wing, or the unit binormal, is moving this way. All right, it's moving down, which is the opposite way that the tail fin is pointing. All right, the tail fin is pointing in this direction, up, which is the opposite of the way that the wing, or the unit binormal, is moving. Okay, so hopefully that helps you visualize what's going on here when we're measuring that twisting for torsion. When the plane or the TMB frame twists, the change in the direction of the twisting, or the change in the unit binormal vector, is in the opposite direction of the unit normal. All right, that is exactly what I just demonstrated. Okay, so to be clear, the degree of twisting, or the measure of torsion, is not just the magnitude of dB ds like you might expect. If you're thinking back to how we measured curvature, you might remember that it was just the magnitude of the change in the unit tangent vector. That was true, but in this case for torsion, this would not measure the torsion. Because while the magnitude of the change in the unit binormal vector with respect to the arc length does describe how the unit binormal vector is changing, the unit binormal vector could be changing in a lot of different ways. Taking the dot product of that change with the unit normal vector ensures that we measure only the twisting motion that leads to torsion, as torsion is defined as the change of the unit binormal in the opposite direction of the unit normal. That is its definition. Okay, and it is important to realize here that for this discussion, I am assuming, like most Calc 3 resources do, that we are working with a standard right-handed orientation of this TMB frame. Okay, if you're using left-handed orientation, which not a lot of people do, it's very uncommon, then the way you measure torsion might be a little bit different. But again, that's very rare. This formula right here is how you will calculate torsion in Calculus 3. All right, and do notice that we are taking a dot product here of this derivative of b with respect to s and the unit normal vector. And so remember that a dot product does produce a scalar, right? It doesn't produce a vector. And so this will give us a scalar value or a number that will measure the degree or intensity of twisting for a space curve. Okay, and another note here, a nice connection that you can make to better make sense of this formula and the dot product here is remember that when you worked with the projection of vectors, where you projected a vector in the direction of another vector, or you wanted to measure how much of a vector is in the direction of another vector, that projection formula involved a dot product. The same idea is happening here. Specifically, you can think of the torsion as the magnitude of the projection vector that results from projecting the derivative or change in the unit binormal vector onto the unit normal vector, but of course in the opposite direction. All right, so if you recall from earlier in Calculus 3, when we learned about projection vectors, this is one of the formulas we learned for calculating the magnitude of a projection vector. We called it component projection. The magnitude of the projection vector of a vector v onto a vector u was equal to the dot product between those two vectors divided by the magnitude of the vector being projected onto. So in this case, the torsion is equal to the negative component projection of dB ds onto n. All right, it's negative because we want it in the opposite direction. But using this formula, we do get negative dB ds dot the unit normal vector divided by the magnitude of the unit normal vector. But the unit normal vector is a unit vector, so its magnitude is just 1, which means we don't have to worry about that denominator. And so that's how we get to this formula up here. Okay, so again, I hope that puts into perspective what this formula represents and where it comes from. A lot of times you'll be given this definition with no reasoning behind it. So hopefully now you have a better idea of what's going on with this definition of torsion. Okay, so to summarize, here's what we've looked at so far. The definition of torsion looks like this. For a smooth curve given by a vector function, r of s, where s is the arc length parameter, so our vector function is in terms of the arc length parameter, for that vector function, the torsion at s is found using this formula. The torsion, or tau, is equal to the negative dot product of dB ds and n, where b is a unit binormal vector and n is a unit normal vector. All right, and of course this right here represents the derivative of the unit binormal vector with respect to s. All right, but now when you actually want to calculate torsion, similar to curvature, we really don't prefer to work in terms of the arc length parameter s. In most cases, that's going to be pretty inconvenient. So instead, we are going to want to find an alternative way to calculate torsion, specifically a way that we can work in terms of any parameter, not just the arc length parameter. And so really what we want here is a way to calculate torsion in terms of our other parameter t. That is not the arc length parameter. And so thankfully, there is a way to do that, but we need to make some changes to this definition. So let's take a look at that next. The first thing we're going to do to change our torsion definition to be in terms of t is rewrite the derivative of the unit binormal vector with respect to s. All right, and so remember that that would come from this vector function. You would have vector b of s, all right, this is before you take the derivative, you would have vector b of s. And another way that you could write that is like this. Remember that the arc length parameter is a function in terms of t, right? When you reparameterize a vector function, what you have to find is the arc length parameter s in terms of t, for which then you would solve for t, and then you can rewrite everything in terms of s. That comes from that arc length function s of t. So you could also rewrite the unit binormal vector in terms of s like this. You'd have vector b of s of t. All right. So now, when you take the derivative of the unit binormal vector, you can view it as a chain rule. You have a regular function inside a vector function, and so you would use the chain rule for that derivative. And so if we take the derivative of the unit binormal vector here, specifically in this form, if you take its derivative, you could technically say that it is in terms of t because you have b of s of t. So you'd have the derivative of the unit binormal with respect to t, so dB dt, and that would be equal to the derivative of the outside function. And for this, we're going to keep it in terms of s, so we're just going to look at it as b of s, and then we'll take the derivative of the inside function s of t. So you'd have dB divided by ds, and then you would multiply by the derivative of the inside function, which would be the derivative of s with respect to t. So you'd have ds divided by dt. Okay, and that should make sense because these ds's could cancel out and you'd just be left with dB dt on both sides of the equation. So this equation is true. But the reason why this is helpful is because now we can solve for dB ds in this equation, because that's what's in our torsion definition here. We're trying to rewrite that in terms of t in some way, and this equation is going to help us get there. All right, so if you solve for dB ds, you need to divide both sides by ds dt, and so that looks like this. dB ds is equal to dB dt divided by ds dt. All right, so you have dB dt divided by ds dt. All right, and so now rewriting this, the numerator dB dt, that would just be the derivative of the unit binormal vector with respect to t. So we could rewrite that like this. I'll represent that with b prime of t, the derivative of the unit binormal vector with respect to t. But what about the denominator? What is ds dt? What would that be equal to? Well, if you remember back to the curvature lesson, we did a very similar process to what we're doing right here to find the curvature definition in terms of t. You may remember that ds dt is just equal to the magnitude of the derivative of the vector function. But if you don't remember where that comes from, this comes from when we first learned about the arc length parameter. Remember that s of t, the arc length function, is equal to the integral from some lower bound of a to t of the magnitude of r prime of t, but we like to write it as r prime of u for this formula, so we don't confuse it with this t in the upper bound of the integral. So you have the magnitude of that vector, and you're integrating with respect to u. But then, remember that we have ds dt, we're taking the derivative of the arc length function with respect to t. So if you take the derivative with respect to t of both sides of the equation, what ends up happening here is the fundamental theorem of calculus comes into play for this side of the equation. The derivative and the integral will cancel out, just leaving you with the integrand in terms of that upper bound of t. And so what we find here is that ds dt is equal to the magnitude of r prime of t. All right, the derivative of the arc length function with respect to t is just the magnitude of r prime of t. So that's what goes into the denominator of this expression that represents the derivative of the unit binormal vector with respect to the arc length function, but in terms of t. All right, so down here in the denominator, we have the magnitude of r prime of t. Okay, so now we have an expression in terms of t that represents dB ds, and so we can replace that in our torsion definition, and we get this. The torsion is equal to the negative derivative of the unit binormal vector, b prime of t, divided by the magnitude of r prime of t, and then you're taking the dot product with the unit normal vector, which now you could just write in terms of t instead of in terms of s, as it would have been before. All right, up here, it would be in terms of s, but if you just find the unit normal vector in terms of t, then you can use this formula instead. Okay, we couldn't just do that for the derivative of b, because it is specifically the derivative with respect to the arc length. That is very important to the definition of torsion, and so if you're going to represent that derivative with some other parameter, you do have to rewrite that derivative to take into account that it is with respect to the arc length. All right, but then once you have that expression in terms of t, you can take the dot product with n in terms of t. Or another way that I like to write this, since the magnitude of r prime of t is a scalar, I'm just going to pull that outside of the dot product between these two vectors. And so I think a better way to write this is that the torsion is equal to -1 divided by the magnitude of r prime of t multiplied by the dot product between b prime of t and n of t, the unit normal vector. All right, that is the definition of torsion, but written in terms of t instead of in terms of the arc length parameter s, like how I originally introduced it. And so you could certainly use this formula to calculate torsion for a space curve, but realistically, it's not always going to be super easy to find the derivative of the unit binormal vector in terms of t. All right, I don't know if you remember, hopefully you do, but when we were finding the general TNB vectors for a TNB frame of space curves in previous videos, that took a lot of time. And sometimes finding the unit binormal vector in terms of t is extremely inconvenient. It takes a long time, or it's just a complete mess to get to. And so needing to find that every time so that you can then take its derivative in order to find torsion is not ideal. This is not something that we want to do, really. This formula would work, but it's ultimately not too useful for us doing these calculations by hand. And so what we use more often is another formula that results from this formula that we just found. And it looks like this. I'm going to erase our work up here and write down this formula. The way that we are mainly going to calculate torsion is with this formula. The torsion tau is equal to the cross product between r prime of t and r double prime of t, dot product with r triple prime of t, all divided by the magnitude squared of the cross product between r prime of t and r double prime of t. Okay, this is the torsion formula that you are going to use more often than anything else. And in this video, I'm not going to show you the proof for this formula, how you get from here to here, because it is quite lengthy and ultimately not really necessary for you to see in order to use the formula. The proof also sort of detracts a bit from the focus of this video or the focus of this lesson, so I'm not going to take the time to show that here. But if you are interested in the proof, if you do want to see how you go from this formula to this formula, I will have a video for that on my membership site So feel free to look into becoming a member if that's something you want to see. I'll have a link for that in the description of this video. Okay, but back to this formula here. Notice that in the numerator, we have a triple scalar product. All right, it's been a while since we've done one of those. We talked about triple scalar products early on in Calculus 3. Essentially, all they are is when you take the dot product of a cross product with another vector, which is exactly what's going on in the numerator here. To calculate torsion in terms of t, we can just take the derivative of our original vector function 3 times, right? We have r prime of t, r double prime of t, and r triple prime of t, and then perform a triple scalar product between them and divide it by the magnitude of the cross product between these two vectors squared. All right, so using this formula is going to be a whole lot easier than using this formula in the majority of cases. Even though a cross product can get pretty messy with some vector functions, you're ultimately going to have an easier time calculating torsion this way than if you were to try to find the unit binormal vector and then take its derivative so that you can take a dot product between that vector and the unit normal vector, okay? You're going to have a much better experience calculating torsion with this formula for the majority of problems that you will encounter. Okay, and so to summarize, our formulas for torsion look like this. For a smooth curve given by a vector function r of t, the torsion at t can be calculated with either one of these two formulas. This right here is the definition of torsion, but in terms of t, you have that tau is equal to -1 divided by the magnitude of the derivative of the vector function, and that is multiplied by the dot product between the derivative of the unit binormal in terms of t with the original unit normal vector in terms of t. But most commonly, you will use this formula, where tau is equal to the triple scalar product between the first, second, and third derivatives of the vector function, and then that is divided by the magnitude of this cross product squared. Okay, and so now that you have been fully introduced to the definition of torsion, as well as some formulas for calculating torsion, let's actually take a look at an example where we find the torsion of a space curve. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. For this example, we want to find the general expression for torsion and the torsion at t equals 1 for this vector function. We have r of t is equal to t cubed I plus t squared j plus t times k. All right, so what that means is we first want to find a representation of torsion in terms of t, and then once we have that, we'll plug in t equals 1 to get the specific measure of torsion at the point corresponding to t equals 1 on this space curve. All right, and so here's the formula we're going to use. Tau is equal to the cross product of r prime and r double prime, which you will then dot product with r triple prime divided by the magnitude squared of the cross product between the first and second derivatives. All right, this is the formula you should always use, unless you were told otherwise to use the definition of torsion for some reason. Okay, and so since we are going to use this formula here, we will need to know what the first, second, and third derivatives are of our vector function. So let's start by finding those. Beginning with the first derivative, r prime of t, you want to take the derivative of each of these components. So we'll have 3t squared times I plus 2tj plus k. All right, we just use the power rule for derivatives in each case. Multiply that 3 down, subtract 1 from the exponent, 3t squared. 2 multiplied down, subtract 1 from the exponent, 2t. And the derivative of t is 1, so you just get k. All right, so now let's take the derivative again. We need the second derivative, r double prime of t. That will be equal to the derivative of these components. So using the power rule for derivatives again, we get 6t times I plus 2j plus 0k, right? The derivative of 3t squared, 2 times 3 is 6. Subtract 1 from the exponent, t to the first power. 2t, the derivative of t to the first power, will just be its coefficient of 2, and 1 is a constant, so the derivative is 0. All right, and then finally, let's find the third derivative, r triple prime of t. Taking the derivative of these components again, derivative of 6t is 6, the derivative of 2 is 0, and the derivative of 0 is still 0. So we get 6i plus 0j plus 0k. All right, so there we have it. We have the first, second, and third derivatives of our vector function, which are all the vectors we need to calculate torsion. But now what we have to do is perform a triple scalar product and then divide by the magnitude of the cross product from that triple scalar product. Now, you have a couple options of how you could go about this here. Remember from when we first learned about the triple scalar product that you can essentially take the matrix that you would set up for a cross product, but actually use all 3 rows of that matrix for the components of the 3 vectors. All right, you wouldn't have a row of I, j, and k. Okay, so for a triple scalar product like this, you could set it up like this. The first row would be the components of r prime of t, the middle row would be the components of r double prime of t, and the third row would be the components of r triple prime of t. And then you would just calculate a cross product as normal. All right, so your setup would be 3t squared, 2t, 1, and then 6t, 2, 0, and 6, 0, 0. You could do that and it probably wouldn't take too long, but my recommendation here is to not do this, but rather calculate this cross product and then take the dot product, because you have to take the magnitude of this cross product anyway. So in order to do that, you have to know what this cross product is equal to. All right, so rather than do a triple scalar product and then do another cross product, I recommend that you just calculate this cross product and then calculate its magnitude and take the dot product with the third derivative, which is not all that difficult. Remember that a dot product is just taking the sum of the product of the vector's components. Okay, so instead of calculating a triple scalar product, I would just calculate the cross product of r prime of t and r double prime of t. So setting up that matrix, we'll have I, j, and k, and then the components of r prime of t and r double prime of t. So we get 3t squared, 2t, 1, and then 6t, 2, and 0. All right, so now calculating the cross product, we'll cover up the I column and calculate a 2 by 2 determinant. 2t times 0 is 0, minus 1 times 2, which is 2. So we get negative 2 for the I term. Then for the j term, cover up the j column, calculate another 2 by 2 determinant. 3t squared times 0 is 0, minus 1 times 6t. So we get negative 6t, but remember that you do subtract the j term, so you have minus 6tj, which means that those negatives would cancel out, giving you positive 6t. So I'm going to make that change right now. We get plus 6t times j, and then we have plus the k term, so cover up the k column. 3t squared times 2 is 6t squared, minus 2t times 6t, which is 12t squared. So that looks like this. We have 6t squared minus 12t squared times k. And then 6t squared minus 12t squared is negative 6t squared. So the cross product here is negative 2y plus 6tj minus 6t squared times k. All right, so that's the cross product between the first and second derivatives of our vector function. Now what we need to do is 2 different things. We need to take the magnitude of that cross product and then also calculate the dot product between that cross product and the third derivative, which that one's not going to be too bad. Let's start with that. It's pretty simple. Notice that 2 of the components of the third derivative are 0. So really, 2 of the parts of the calculation for the dot product are just 0, right? Because you take the sum of multiplying the corresponding components. You would take negative 2 times 6 plus 6t times 0 plus negative 6t squared times 0. And 2 of those are just going to be 0. All right, so here's what that looks like. The dot product between the cross product of r prime of t and r double prime of t with r triple prime of t will be negative 2 times 6 plus 6t times 0 plus negative 6t squared times 0. Both of these 2 terms become 0, and so we are just left with negative 12, because negative 2 times 6 is negative 12. All right, so now that is what goes in the numerator of our calculation for torsion. That whole thing in the numerator there, this triple scalar product, just becomes negative 12, even when you're working in terms of t. All right, that's still part of the general expression. We haven't done anything with this t equals 1 yet. We're going to hold off on that until we get torsion in terms of t. But the other thing we still haven't done is find the magnitude of this cross product. So let's do that. The magnitude of the cross product between r prime of t and r double prime of t will be equal to the square root of the sum of the components squared. Negative 2 squared is 4, so we have 4. And then you want to add that to 6t squared, which gives you 36t squared. And then you want to add that to negative 6t squared, but squared, so you get plus 36t to the power 4. All right, now there is a common factor here that we can pull out. 4 and 36 can all be divided by 4, which is a perfect square. So this would be equal to the square root of 4 times 1 plus 9t squared, right? 4 times 9 is 36. So if you pull out 4, you're left with 9. And then you also have 9t to the power 4. And then taking the square root of both parts, the square root of 4 is 2. So really what you get here, and I'm just going to rewrite it right here, is you'd have the square root of those terms and then 2 on the outside because the square root of 4 is 2. All right, and there's no way to further simplify this. This expression cannot be factored in any way. Okay, so now we have the magnitude of the cross product between the first and second derivatives, and we have this triple scalar product. Now we just have to put both of those two things into our torsion formula to get our general expression for torsion of this space curve. All right, so let's do that. The torsion will be equal to our triple scalar product, which resulted in negative 12, divided by the magnitude of this cross product squared. So we're going to square this expression. All right, so we have 2 times the square root of 1 plus 9t squared plus 9t to the power 4. And we're squaring that. And so moving down here, the torsion would be equal to negative 12 divided by 4 times 1 plus 9t squared plus 9t to the power 4. Right? If you square the denominator, 2 squared is 4, and if you square this quantity, it just cancels out with that square root, so you're just left with what was inside the square root. But then we can simplify further, because negative 12 is divisible by 4, you'll get negative 3, so our final answer here for the torsion as a general expression for our space curve is negative 3 divided by 1 plus 9t squared plus 9t to the power 4. All right, that represents the torsion. So for any value of t that corresponds to a point on the space curve, you can plug that value of t in and get the corresponding measurement of the torsion or the intensity of the twisting at that point along the space curve. And that's exactly what we're going to do now, specifically for the point t equals 1. Right? That's the last part of this example. We found the general expression for torsion. Now we want to find the specific torsion at t equals 1. So plugging 1 in for t here, and you could even write it like this. You could have torsion evaluated at 1, because technically this would be a function, right? Torsion is a function in terms of t. So torsion evaluated at 1 is equal to negative 3 divided by 1 plus 9 times 1 squared plus 9 times 1 to the power 4. But 1 squared and 1 to the power 4 is just 1. So you have 1 plus 9, which is 19. So you get negative 3 divided by 19. That right there is the specific measurement of torsion at t equals 1 along this space curve. That gives you the measurement of the intensity of the twisting on this space curve at the specific point corresponding to t equals 1. Okay, and so that's how you find torsion. That's how you use this formula to find a general expression for torsion as well as a specific value of torsion for a space curve. And if you want to get more practice with this formula, you will be able to do so in the examples video for this topic. But before I end this lesson, there's one more thing I want to show you, because now that we know how to find both the curvature and the torsion of space curves, we can take a look at what are known as the Frenet-Serret formulas. We found T and B frames, or Frenet-Serret frames, in previous videos, but what we're going to look at now is a little bit different. The Frenet-Serret formulas relate the derivatives of the vectors from a T and B frame to the curvature and torsion of a space curve. or really what the formulas do, is describe how a TMB frame is changing as it moves along a space curve. In fact, you've technically already seen one of these formulas before. If you recall from the very end of my lesson on TMB frames, we looked at the relationship between TMB frames and curvature, specifically a way that you could rewrite the unit normal vector in terms of the arc length parameter using the curvature k. We said that the unit normal vector in terms of s is equal to 1 divided by the curvature times dt ds, or the derivative of the unit tangent vector with respect to the arc length parameter. If we solve for that derivative, dt ds, this is what we get. You would want to multiply both sides by the curvature, giving you that dt ds is equal to curvature multiplied by the unit normal vector. And I'm just going to keep it like that. We're going to assume that for all of these formulas, that our TMB vectors are in terms of s, the arc length parameter. Okay, but what we have right here is the first of the 3 Frenet-Serret formulas that help us describe how the TMB vectors are changing for a TMB frame. In particular, this formula specifically is telling us how the unit tangent vector is changing with respect to the arc length, or the derivative of the unit tangent vector with respect to s. It says that it's equal to the curvature of the space curve multiplied by the unit normal vector. All right, so now we need 2 more formulas. We need one that helps us describe how the unit normal is changing, and another one helping us describe how the unit binormal is changing. And we're actually going to start with the unit binormal. You might expect that we would look for the derivative of the unit normal next, but we're going to come back to that because its result is easier to come to if we first find the formula for the unit binormal vector. All right, so we'll come back to the unit normal, but for the unit binormal, remember that this is how we define it. The unit binormal vector is equal to the cross product between the unit tangent and the unit normal. And so what we're going to do here is take the derivative of the unit binormal. And by the way, once again, all these vectors we are assuming are in terms of the arc length parameter s. So if we take the derivative with respect to s of both sides of that equation, we'll get this. You'll have dB ds is equal to the derivative dds of a cross product between the unit tangent and the unit normal, okay? Now this is where things get a little bit tricky. You have to remember one of your properties for taking the derivative of vector functions. Specifically, there is a property for when you take the derivative of the cross product between 2 vector functions. And essentially, you can think of it as a product rule. You take the first vector and cross it with the derivative of the second, and then you add that to the derivative of the first crossed with the original second. All right, and the order does matter there. So be careful. Here's what we get. dB ds is equal to the original first vector function, vector t, cross the derivative of n with respect to s. So we have dn ds, and then we add that to the derivative of the first vector, or the derivative of the unit tangent. So you have dt ds, and that is crossed with the unit normal vector. All right, the original second vector function. So that right there is what dB ds is equal to. But our end goal here with these Frenet-Serret formulas is to represent the derivatives of our TMB vectors in terms of those vectors themselves and curvature and torsion. All right, so we need to make some adjustments to this formula. We don't want to have these cross products in the formula for dB ds. And so the first thing that we can do here, notice that we have dt ds, and we already know what that's equal to, right? We know that dt ds is equal to the curvature k times the unit normal vector. So we can just straight up rewrite that here. The first cross product remains the same. You still have t cross dn ds, so I'll write that in here. But then you're adding that to dt ds, which is the curvature times n. So we have the curvature times n cross n. Okay, and this is interesting because it doesn't matter that we're multiplying n by a scalar value, which is the curvature. That doesn't change the direction of the unit normal vector. It just changes its length. So this vector, the curvature times the unit normal vector, is still pointing in the same direction as the unit normal vector, right? These 2 vectors would be parallel. And so since they are parallel, their cross product is 0, right? That's one of the properties of the cross product. If you take the cross product of 2 vectors that are parallel, the result will be 0. So this right here becomes 0 because we have parallel vectors. which means if we continue our work up here, dB ds is just equal to the unit tangent cross dn ds. Okay, so we got rid of one of those cross products, and so our formula is simpler, but we still want to get rid of this cross product somehow. We don't want to define the derivative of the unit binormal using another derivative. That's not going to be helpful. We want to write everything in terms of the original vectors and curvature and torsion. And so we have to think a little bit outside the box here on how we can rewrite this formula. And so here's our thought process. Remember that the unit tangent vector and the unit normal vector are perpendicular, right? That's true of all of the TMB vectors in a TMB frame. They're mutually orthogonal or all perpendicular to each other. And it would also be true that the unit normal vector would be perpendicular to its derivative, right? It would be perpendicular to dn ds. That comes from one of our properties of the derivative of vector functions. If a vector has a constant length, which the unit normal vector does, its length or magnitude is 1, then it will be perpendicular to its derivative. Okay, that's just one of the properties of vector functions. So we know that these two things are true. Both the unit tangent vector and the derivative of the unit normal vector are perpendicular to the unit normal vector. So what that means is that their cross product would be parallel to the unit normal vector, right? Just think about it like this. If you have two vectors that are perpendicular and you take their cross product, you have to get a vector that is perpendicular to those two vectors. All right, it would give you a vector like this. That is the vector that is perpendicular to both of those vectors. So if you think of this vector as t and this vector as dn ds, they're both perpendicular to the same vector, then their cross product must be parallel to that vector. It only makes sense. It might point in the other direction, but it will be parallel to the vector that they are both perpendicular to, which in this case is n. All right, so here's what we know. We know that the cross product between t and dn ds is parallel to n. All right, which means that it would also be parallel to any scalar multiple of n, because multiplying a scalar by a vector does not change its direction. So this cross product, it's parallel to n, which means that it would be equal to n multiplied by some scalar value. All right, the cross product between t and dn ds would be equal to some scalar, I'm just going to call it c, multiplied by the unit normal vector. This has to be true because this cross product is parallel to n. Some scalar multiple multiplied by n would have to be equal to this cross product. All right, so now here's the punchline. Remember that this cross product, we said it's equal to the derivative of b with respect to s. So if we write that in here, we have db ds, and it's equal to some scalar multiplied by the unit normal vector. So we have c times n. If you take the dot product of both sides of the equation with the unit normal vector, right? If you do dot n on this side of the equation, and you do dot n on this side of the equation, the dot product of a vector with itself is just equal to its magnitude squared. And in this case, the unit normal vector has a magnitude of 1, so it would just be 1 squared, leaving you with just a constant of c that is equal to the dot product between dB ds and n. And my question to you is this: does that look familiar? Because it should. We looked at this at the very beginning of this video, or at least something that looks very similar to this. Remember what we defined torsion to be. We said that the definition of torsion is that torsion is equal to the negative derivative of b with respect to s dot product with the unit normal vector. Okay, and here's that definition. So if we're saying that the positive version of that is equal to some constant, well then that just means that that constant would be equal to negative torsion, right? What we get here is negative tau. That's what that constant would have to be. I hope that makes sense. We have the derivative of b with respect to s, dot product with n. The only difference is that it's positive, not negative, so that means that it would be equal to negative tau, the negative torsion. All right, and so here's why that's important. Going back to this step right here, t cross dn ds, we know that that's equal to dB ds, but it's equal to that constant times the unit normal vector. So really it would just be equal to negative tau, or the negative torsion, times the unit normal vector. That's what we get here. For dB ds, it's equal to the negative torsion times a unit normal vector. That is the Frenet-Serret formula for the unit binormal vector. It describes how the unit binormal vector changes using the unit normal vector and the torsion of the space curve. Okay, so now we have two of the three Frenet-Serret formulas. We just need to find one more, and that is for the unit normal vector. And here's how we'll find that. We're actually going to make use of another cross product. Remember that a TMB frame looks like this. You have the unit tangent, the unit normal, and then the unit binormal, which is perpendicular to both of them. All right, so all three of these vectors are perpendicular to each other. If you wanted to find n, you could take a cross product involving the unit tangent and the unit binormal. But remember that the order does matter. You could certainly use the right-hand rule that I showed you way back in the cross product lesson to figure out how to set this up, but an easier way to go about it is to just look at this TMB frame in a counterclockwise motion, which says that B cross T would be equal to N. That's how I like to go about it. Just like T cross N is B, right? This formula right here, B is equal to T cross N. We do that in a counterclockwise motion. Do the same thing to find N. B cross T is N. All right, so we would say that N is equal to the unit binormal B cross the unit tangent T. And so then what we want to do is take the derivative with respect to S of both sides of that equation, giving us dn ds, and that would be equal to another derivative of another cross product. So we're going to follow that same process we did over here, using that property of the derivatives of vector functions. We take the first vector function, which is b, cross it with the derivative of the second, which is the derivative of t, so dt ds. I'm just going to replace that right away with the curvature times n. All right, we're going to save some time here. You would be crossing it by the curvature times n, which is dt ds, and then you would add that to the derivative of b, or db ds, which I'm going to replace right away with negative tau times the unit normal. All right, so we have minus tau times the unit normal, and then you cross that with the original second vector function, which is t. All right, so we're crossing that with t. And so now for our final steps here, remember that for a cross product, you can pull any scalar value multiplied by either vector out to the front of the cross product. So this would be equal to the curvature times the cross product between b and n, and then you'd have minus tau times the cross product between n and t. And so now, the last thing we need to do is rewrite these cross products. Similar to how we found the cross product for n using our TMB frame, we're going to do the same thing here to see what these two cross products would give us. Because Tn and b are all perpendicular to each other, so if you take the cross product of two of them, you're going to get the one you don't have, but it might be either positive or negative. All right, so b cross n, look at the motion that we are moving here. B cross n is in a clockwise motion. So that's not going to give you t, it's going to give you negative t. All right, remember the cross product result here will be positive when you go in a counterclockwise motion, but from b to n, we're going clockwise, so that results in negative t. Okay, so this is equal to the curvature k multiplied by negative t, and then we are subtracting tau multiplied by the cross product of n and t, and that also moves in a clockwise motion. N cross t will give you b, but it will be negative b because we are moving clockwise. All right, again, you could use the right-hand rule to figure that out, but I think this method is a little bit quicker, so that's why I used it here. We get negative b multiplied by tau. All right, and so now, simplifying, what we find here is that dn ds, the derivative of the unit normal vector with respect to the arc length parameter, is equal to negative k, the curvature, times the unit tangent vector, and then these two negatives will cancel out. So we have plus the torsion, tau, times the unit binormal vector b. That is the last Frenet-Serret formula that helps us describe how the TMB vectors are changing for a TMB frame. All right, specifically using the TMB vectors as well as curvature and torsion. All right, so to summarize, these are the Frenet-Serret formulas. Together, as I just said, they help us describe how a TMB frame changes along a curve using the curvature k and torsion tau, where t, n, and b are the unit tangent, unit normal, and unit binormal vectors of a TMB frame. And of course, all of those vectors are in terms of the arc length parameter s. All right, now unfortunately, or maybe fortunately, depending on how you look at it, we are not going to use these formulas that much, if at all, in Calculus 3. And so maybe you're wondering, well then why did we go over them? And it's because I wanted to show them to you because it nicely wraps up everything that we have looked at regarding TMB vectors as well as just vector functions in general. Okay, this sort of puts together everything we've talked about over the last couple lessons involving our unit tangent, unit normal, and unit binormal vectors, as well as the curvature and torsion. These formulas sort of show you how all of these things are related and how they work together to allow us to do some nice calculations for curves in 3D space. Okay, so really these formulas just serve as a nice way to put a little bow on everything we've talked about up to this point, but it might also serve as a nice introduction for when you might see these formulas again in a future physics or engineering course. All right, because there are more applications of TMB frames and the TMB vectors that can be studied, but the road ends here for Calculus 3. We're not going to go any further with TMB frames or these formulas, but you may certainly encounter them again. Okay, but with that, that is it for this lesson on torsion. If you want to get some more practice calculating torsion, feel free to check out the examples video for this topic. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.